Okay, the second problem this week is problem 9.72, found on page 375. We have a TV station in this case. Last year their viewership was 25%, 0.25 during the 11 o'clock news. They want to do better. They got new talent. I don't know what they did, spent more money. But the question is, did it do any good? Okay, so they went out and took a sample. They asked 400 people if they watched the show. 146 of them said yes. The question is, did they improve viewership, or is it still stuck at 25%? So the first thing we need to do in this case is to state the null and alternative hypotheses. And in words, what we're saying that the null hypothesis is the viewership is stuck at 25% or less. We did nothing to improve things. If we come up with, if our sample data disproves this null assertion, null hypothesis, then we're stuck. We must accept the alternative hypothesis is that no, it's better than 25%. Well, we have to be a little more precise because we're statisticians after all. So what we're really saying is H0 is the p, the proportion p, is less than or equal to 0.25, or the alternative hypothesis, p is actually greater than 0.25. And the question is, does the sample cause us to reject H0, and if so, at what level of significance? Let's just look at the normal distribution curve here. What we're saying is that this test statistic is going to give us a value, a z-value. It'll be out somewhere in this upper regions of the bell-shaped curve. This is a greater than problem, so we're interested in the right-hand tail. And what we're saying with this test is that if we make the assumption that the mean value of the proportion is 0.25, that is, if the null hypothesis is true and the proportion is really 0.25, we're asking what's the probability of drawing this sample of 146 people viewing out of 400. Well, that's going to give us some proportion which is going to turn into a z-value which will be plotted somewhere in this range out here. Now if it turns out that statistic is way out in the tail of this curve, meaning that the probability of getting that kind of sample is very low, if, remember the if on this thing is that we got that sample if we assume that the proportion is truly 0.25. If the probability of getting a sample under that assumption is very low, then we have to reject the assumption that it's 0.25 and accept the alternative. So we're dealing with a single tail, greater than problem, and we have to keep that in mind as we go through the exercise here. Okay, let's start out and calculate where that fence is going to be. First of all, I'm going to bring in the alpha values here. Now remember, this is a single tail greater than problem, so we don't have to worry about dividing alpha into two pieces, a lower tail and an upper tail. We just have one. And we need to know what are the z-values that correspond to 0.1, 0.05, 0.01, and 0.001. Well, we could look them up in the table 6.1, but that means we have to search through and find the one that's closest to 0.1. I'd rather just use Excel. So the formula here is it's equal to the normal standard inverse function. Now, standard means that we're dealing with z-values, not with means and standard deviations. And it also, in the inverse, means that rather than starting with a z-value and finding the probability, we're doing it the other way around. We're starting with a probability and finding a z-value. Now, the other thing I have to note here is that I'm not going to use 0.1. I'm going to use 1 minus 0.1, or B18 in this case, because I'm interested in that right-hand tail. And we know that the table 6.1 and the Excel functions give us the opposite of that. So we're going to take 1 minus 0.1. And that gives us a z-value of 1.28. I can drag this fellow across. And we see that the z-value, the z critical value, goes from 1.28 up to 3.09. So the question is, does the z-test value that comes from our sample give us that kind of number in that range, or is it greater, or is it less? Where does it fall? Okay, so p hat, which is what I'm going to call the test statistic, is really equal to the 146 people out of 400. This is the proportion. 146 out of 400 is our test proportion. 36.365. So on the surface, that looks pretty good. That's a lot bigger than 0.25, but we know we can't be lulled into a false sense of security here because we don't know what the standard deviation is and what the z-value will really come out to be. Well, I don't have a formula to show you here, but you can flip to page 371 and get the formula. I'll just type in the value here that corresponds to each of these alpha to this p hat value, and it's equal. And I have to tell you also, I should also tell you that we ought to keep the p0 value here because that's a factor we'll need. That's the assumed value of 0.25. Okay, so the z-value is going to be equal to the difference between the measured and the assumed divided by what is in effect the standard deviation for a proportion that's equal to the square root of p0 times 1 minus p0 divided by n, which is 400. And that gives a z-value of 5.31. 5.31, that's way off here to the right. It's a probability that's greater than 0.001. If you flip to, oh, I wish I could remember the page number. There's a table in the book that says gives you the level of significance, and it's in chapter 8, and I've meant to have, I'll post the page number, but the question is, what level of significance does this have? In our case, because it's greater than 0.001, the probability is greater than 0.001, that means that it is extremely strong evidence that we should reject H0 and accept H1. Now, if we wanted to carry this out with a p-value analysis, what we would do is take this same z-value that we just calculated and come up with a probability associated with that. And that would be equal to, I'm sorry, I'll do this, 1 minus the normal standard distribution of, now we have a z-value, so all I have to do is start with an equal sign, John, equals 1 minus the normal standard distribution of this z-value, and that gives me a value of 5.4 times 10 to the minus 8. That's a lot of zeros. Believe me. Let's just see how many zeros it really is. If I do this, and look at all the zeros. 0.000000543. That's a very small probability. So there's no way in the world we can believe that this proportion is really 0.25. In fact, if I put it, let's just try a different value. Let's try 0.3. That gives me a value of 0.0022. 0022. So it's somewhere between here and here. So we've gone from extremely strong to, I forget what the other term is, very strong. Be sure to find that table. I wish I could give you the page number here. Maybe I'll find it before we get done. Because it shows up in the quizzes. Just a word to the wise here. And so you want to be sure you at least memorize or remember where that table is better than I have, so that you know what those words are and can answer the quiz questions properly. I'm too old to remember all this stuff from one semester to the next, but you are young folks and you can do it, I am sure. Okay, that's it for this week. Thanks very much, and we'll see you online.